Swayam Prabha. Digital India. Educated India.
Okay, so let's get started again. We've done the hard work. We've sort of laid the foundations, laid the framework for talking about cake cutting, the division of a divisible heterogeneous good. And it's time to sort of reap the benefits and sort of actually see some nice implications, see some nice development of some nice algorithmic ideas. So just to, again, like warm up our proof engines, let's start with a simple claim, and I'll need your help in actually proving this sort of claim. I'll not even call it a theorem, it's just a claim. So the first one is that NV freeness implies proportionality. Again, I'm not going to sort of keep repeating the fact that we are going to work with the setup with evaluation functions satisfy three assumptions. What were they? We had three assumptions on the evaluations, at least. No? So the evaluations are non-negative, they are divisible and additive. So if I take intervals, they just sum through it up. Like the value of two disjoint intervals was the sum of those two. So is that sort of fresh in everyone's mind, or should I sort of go back to? Yeah, so here they are. Non-negativity, divisibility and additivity. Sort of the somewhat atypical one might be the divisibility, which says that if I take any interval, there's a meaningful way in the valuation terms to say half this value or 1/3 this value or lambda times this value for any lambda between 0 and 1. So that's an assumption that we'll make, and as we discussed, this sort of rules out point masses, this rules out these degenerate cases where the value sits on a specific point, the entire value lies on a diamond that's sort of been plugged into the cake. So with these three assumptions, under these assumptions, I would want to prove that for general cake cutting setup, so for any number of agents, NV freeness, that is the second solution concept, which says that everyone is satisfied with its own interval, actually implies proportionality. So this second comparative notion of fairness actually is stronger than the first one in this sense. Okay, so here comes a proof. So the first one is that like we fix an NV free allocation. So we have these intervals, the subscript tells me which agent receives it. So again, note that this I here is not really a numeral in that sense, it's just the identity of some agent. So I have say this is I7, this is I3, sounds like iPhone models, I10, why not, so on. So every agent gets one of these intervals, this partitions the whole cake, and I'm assuming that this is an NV free allocation. Note that this is sort of a leap of faith. I haven't actually proved to you that such things always exist. So that's something I'm kind of shrugging under the carpet for now. We'll get to it sooner than later. But say there is an NV free allocation. There's this partition I1 through In. These intervals are NV free, i.e. they satisfy the second property for all pairs of agents. So now the first thing I'll note is that I'll also fix an agent I, right? So pick any agent, 1 through n, up your choice, it's the identity of the agent. So first of all, note that I can write, so if I sum over all these n intervals, so I'm looking at the value of I. right? So Vi, the value of I. Now I'm looking at the value that I has for all of these intervals. So I just sum these numbers up. So Vi has some value for the first interval I7, she has some value for the second interval I3, so on and so forth. So I'm just looking at this sum. So my claim to you is that this is nothing but the value that I has for the whole cake, for the whole 0, 1 segment. Why is this true? It's a magic word I'm looking for, starts with an A. It's additive. Valuations are additive. This is a partition of the whole cake. The value of this entire union is just the sum of the values individually. And what is, by normalization, what is the right hand side? It's 1. I've normalized it to 1. Okay, so far so good. So all this says is that if I looks at the entire division, looks at the value it has for all the sort of intervals, sums it up, it comes to 1. Fine, it's additive, has to happen. Okay, so this actually holds true for any partition of the cake. I have not used NV freeness. This is just a consequence of additivity. It's just a property of the valuation function. So now I'm going to, for the first time, invoke the fact that this allocation, this n partition of in intervals, is NV free. So what does this mean? This just means, by the definition of NV freeness, is that I have the value that I has for its own interval is at least the value that I has for any other interval. So this is for all and again let me repeat that I don't really have to be explicit about the fact that I is not equal to j. When I is equal to j is equal to I, so there's an equality. So again, this inequality holds true. Okay, so as someone had already pointed out, this is pretty much all I need. What do I do now? Can someone suggest the next step forward? It's kind of suggestive the way like I've written it in a suggestive manner, like this is right below, like Vi, Ij are vertically aligned. This is true for all j's, yes indeed. Perfect, yeah. So, I mean, the single word answer is I just sum these inequalities up over all j's, right? So, I will erase this to create some. So, all I'm doing is I'm fixing an I and I'm summing this inequality across all j's. So, there are n possible j's, which includes I itself. But what I'll get is n times Vi of II, because the left hand side stays the same. I is always comparing with its own value, is at least this I know is exactly equal to 1. It's written right here. So what does this tell me? This tells me that if I look at the value that I has, again dividing both the left hand side and the right hand side by n, which is I get this. So what does this tell me? Well, this tells me that the inequality required for a proportional fair division, required for proportionality, actually holds for all I. I mean, I can repeat this argument for any I. There you go. So this essentially tells me that NV freeness is a stronger solution concept than proportionality. In particular, it tells me that if I give you an allocation that's NV free, it has to be proportional. So again, let's circle back and notice one thing. I have established it for the case where every agent receives a contiguous part of the cake. Every agent receives an interval. It's a good exercise for you to say that this again holds even if the agent gets like disjoint intervals, as long as I have NV freeness across these crumbs assigned to different agents. Again, the same argument verbatim kind of holds. So this NV freeness implies proportionality even if in this sort of more general setup where I'm not forced to assign a contiguous part of the cake, where I'm not forced to assign a single interval to each agent, right? So this is sort of, yeah, think about it as you're walking back to your, well, you don't even have to that much time, just think about it as you're climbing down the stairs. Okay. So that kind of establishes the first claim. And pictorially what this means is that if I look at the space of, so if I look at the space of all, so all allocations, so how many allocations will there be if I give you a cake? Can I put a number on this? What is, like, is this a finite set? It's an infinite set. How many ways can I divide a cake into n disjoint intervals? What is that? Infinite, right? I mean, they're cuts, I can place them anywhere. So, I mean, the equivalent way of thinking, you can uniquely associate with each allocation, in some sense, a probability vector. Will bank on this sort of mapping sooner than later, but yeah, this is an infinite set, a lot of them. And then in this space you have proportional ones that satisfy the first inequality that every agent gets 1 over nth. Note that again, I have not actually proved to you that this is a non-empty set. For all we know, there might be a cake cutting instance, there might be such complicated valuations which, while satisfying the 3 assumptions, lead us into a scenario where I can never find a proportional allocation. So for all we know, this set might be empty, but let's just say it is not, and we'll prove that it's not. But what the previous claim tells me is that the picture looks like this. I have all allocations, some of them are fair in the sense that they are proportional, and then there's an even smaller set which are NV free. So if you are here, if you give me an allocation that's NV free, it's guaranteed to be proportional, and hence I have this sort of containment. What's non-trivial and which will take us some sort of mathematical machinery is to prove that even the innermost set here, the set NV free, they always exist. So these sets are non-empty. What we will do now, moving forward, is to actually show that this set right here, the set of proportional fair divisions, is actually non-empty, and we'll do it sort of the way we like. We'll do it constructively via an algorithm. So that's the first item on our agenda. We'll try to prove that given a cake cutting instance where the evaluations satisfy 3 assumptions, you will always have a proportional fair division. Okay, so before actually moving on, here's sort of a exercise. So when you have, for the special case of 2 agents, when n is 2, when you only have Abraham and Lot, then a proportional allocation is actually also NV free. You will again need to use the 3 properties. Simple exercise, think about it. I'm sure if there are questions we can sort of circle back to it, but yeah, it's kind of a simple jugglery. Okay, so this says that the converse is true. Converse of the previous claim is true for 2 agents. We'll see why 2 is sort of the right number as soon as we go beyond 2. This claim actually does not hold true. We'll see an example to begin with. So when you have more than 2 agents, I'll now give you a very specific example wherein the converse is not true, i.e. I'll give you an example where there is an allocation that's proportional, that's a proportional allocation, but it's not NV free, right? So again, this is for n more than 2, and this is for this is true in general. So what this says is that there are cases where you have allocations right here. The allocations that live, they are not NV free, so outside this innermost set, but they are still proportional, so contained in the sort of second level of the onion. Okay. So why can't I claim that there are instances where no proportional is NV free? Just like almost a trick question, but yeah, let me just see why that is. I'm claiming that armed with whatever we have discussed so far, the following statement is blatantly false, that there are cake cutting instances wherein if you take any proportional allocation, then that is not NV free. Yeah, I'm assuming that set of NV free allocations is not empty. Well, if that's the case, then these two would not intersect, right? But I've already told you that the innermost is always a subset of proportional, so cannot be. They always have, there always is, like, again, modulo this fact, that non-trivial fact, that NV free always exists. You just take an NV free allocation, it's guaranteed to be proportional. So that right there is an allocation that's proportional and NV free. So sort of the example I'm going to tell you is that there are some proportional allocations that live here, i.e. that are not NV free. Yeah, it's just the two solution concepts. I'm sort of hammering it in again and again before we go to algorithms, so that sort of it's somewhat internalized and you're comfortable with sort of playing around with two notions of fairness. Like if there are questions, I can sort of address them, but yeah, hoping that sort of the distinction between the two is clear and sort of before we actually get to some algorithmic results. So I'll prove this sort of claim right here through a sort of example. And I'll use this example to actually specify something like, again, something that's used quite often in literature, which is So I'm saying that, look, one way to a specific way, I've assumed these three general properties, but one specific way I can specify the valuation of an agent. So this is certainly a restriction on the model, is that these valuations can come through a density function. So think of like a probability density function sitting on the interval 0, 1. So for agent I, so we have, again, this is sort of restricting the whole setup. It's like looking at a particular class of valuations, if you will. The class of valuations are the ones that are induced through a density function. So for agents, we have some density function which takes a point, every point in the interval, and spits out a real number. So it's a function that just sits on, whose domain is 0, 1. So pictorially, you have the 0, 1 line. This is the density function of I. What do I mean it's the density function? It simply means that if I want to compute the value of an interval, then I just integrate the density function. So I look at the area under the curve, and that tells me the value of this interval. So value of agent I for an interval I is defined to be just the integral of this. So I just integrate over this interval, density function just spits out. So think of it as just the probability density function. Because of normalization, this is indeed a measure. It's a probability density function, right? So in particular, the normalization tells me that if I integrate over the entire interval, this dix dx, then this has to be 1, right? The total value of 0, 1 is 1, which is exactly the left-hand side of this equality. So that's one way, that's one class of valuation functions we can look at, and so we'll say so I look at a valuation function vi, which is induced by this density function di. We'll say that this is piecewise constant if di is piecewise constant. This is just nomenclature, right? I give you a density function that's constant for some time, goes up, goes down, stays constant. It's like a pulse. Such DIs, the valuation they induce, are called piecewise constant. Standard nomenclature. I'm just throwing it out there in case you read some book or text. If this word comes up, should be familiar with it. So again, here's a concrete example. So what I'm drawing here on the y-axis is the value of di. Picture isn't great. Let me try again. Okay, this is constant up to Picasso. So say here it's 0 for some time. It's 3/4. So this is the density function. It's the value. So if I pick any point between 0 and 1/4 here, the value of the density function is 1, and say it's 0 again between 1/4 and 3/4, and now say again it's constant again between 3/4 and 1, and someone sort of tell me what the value of the density function has to be. So I'm saying this is constant again. So what should be the value here? What's the height of this tower? 3. Anyone else? Can someone explain this to me? Right. What's the value of the interval for this agent I? What's the value of the interval 0 to 1/4? What is that? 1/4. Why is that? It's just the area under the curve, right? This is integrated. So the total value has to be 1. So what's the value in this right here, in this total value that I must sort of push into this? What is that? 3/4, and the sort of base is 1/4, so the height has to be 3. This is 3, like di here is 3, di here is 0. So it's just a piecewise constant function, a bunch of towers, and the way I find a value is just integrate. Okay, so with this, again, the purpose of this is to sort of, again, give you like some piece of nomenclature that shows up in literature. It's kind of standard enough for you to know, and more often than not, you can find good examples just working with such valuations that are induced by piecewise constant functions. Another sort of advantage of such valuations is that I can give them to you as explicitly give them to you as inputs. Note that the level of generality in which I've defined the valuation function, it's not obvious, right? Like it's a value for every interval. So I want to feed it into a computer program. How do I do it? Like again, there are infinitely many intervals. Even with the 3 properties, it's not obvious if there's a succinct way for me to actually give it as input to a particular program. In contrast, if the valuation function is piecewise constant, i.e. comes from such density functions, then I can give it as input it as an input to a particular program by just specifying these breakpoints and the heights of these. So I can give this density piecewise constant density function, input it into a program. So that's another sort of advantage of this valuation class. They can be sort of handed over to a piece of software explicitly. Okay, so now with this sort of digression, let's get back to the task at hand, and I would like to now prove or through an example, establish through an example that there are allocations that are proportional but not NV free. Okay, so here we go. So I have n agents, so n more than 2. So it's sort of overload, but I hope this is not point of confusion that I'm using both 1 through n to index the agents and to count the number of agents. It's just kind of it's a notational ease, if you will. So here's the thing. So in this example, the density functions are actually completely complementary. That is, if I look at any point in the interval, only one agent, uniquely one agent will actually have non-zero value for the density function. So what do? Here's a simple idea. So this is the halfway mark. The cake is lengthwise equal on the left and the right. Now I look at small intervals of length, say 1 over 2n, right? So this right here is the length of the interval, and this is, say, valued by agent 1, and the density value is exactly 2. So this is for agent 1. So what's this is only for agent 1. So D1 subscript means it's the density function of agent. So what's the value that agent 1 has for this tiny piece of cake of length 1 over 2n? What's the area under this curve? It's 1 by n. So if in particular I've designed it such that if agent 1 gets this tiny piece, proportionality is achieved. So that's pretty much what I'm doing. And again, I'll kind of repeat it. So I look at the next interval again of length 1 over 2n, and now it's agent 2's turn. So D1 kind of drops to 0 here. It's only D2 that stays at 2. And so 2 values this piece again at 1 over n. So the density is 2, the length is 1 over 2n, I multiply the 2, the area under the curve, like integrate, I get 1 over n. So these are very nice and accommodating agents, as in they don't fight with each other, they're so good friends. One likes chocolate, the other likes strawberry, just kind of separate themselves out. So this story repeats till half. So here it's dn, and again the value is 2 and the length is 1 over 2n. The choice of the length ensures that if I run over all n agents, this will actually, so far the construction will stop at 1/2. So n times 1 over 2n is half, so this is exactly why I picked this length. So note that it's quite nice and sort of good to go. So this is, if I haven't completed the valuation, let me do it now. So I have half of the length left, and for each agent I have 1 over, so just a calculation, so I have 1 minus 1 over n value left for every agent, 1 over n has been consumed. So, and kind of divide it uniformly in this range of 1 through 1/2, so I kind of double it actually. So on the left half, they are completely accommodating. On the right half, they are completely competing. Just everyone wants it, and it's just slightly below this. Note that what's the total value for any of the n agents for this right half of the cake? The length is 1/2, density is this, you multiply, you get 1 minus 1 over n, which summed up with 1 over n is exactly 1. It's a tailor-made example for satisfying all these properties. Now my claim to you is that there's an obvious allocation here which is proportional but not NV free. Can someone quickly point it out to me? So I actually want contiguity. You're right, that will work too, but agent 1 gets disconnected pieces. But here's my like proposed allocation. Agent 1 gets this, the tiny piece of 1 or 2n, designed to satisfy proportionality. Agent 2 gets this I2, so again the indexing matches, so on and so forth till agent n minus 1. And say I am the last agent, and happily I just walk away with a huge chunk in. So this is proportional. Why can someone, and even better, why is it not NV free? Who's the point of NV for everyone in this example? What is that? The last agent, right? Because I mean, so if it's proportional, because if I look at VIII, this is at least 1 over n. In fact, for the first n minus 1 agents, this is met with an equality. The nth agent actually gets its total value. So Vn of In is 1. I'm very happy. Almost gets the entire total values worth of cake. But everyone envies In. Right. So if you look at, for example, this is 1 over n, but when one looks at what the last agent has in store, what is this? What is that? 1 minus 1 over n. Okay. Yes, no. I mean, the density function of even agent 1 is this. So this entire piece, so here the density of agent 1 is 0, but this piece is entirely valued by it. Its total value is exactly 1 minus 1 over n. And of course, I have the property that n is strictly more than 2. So this thing right here is more than, if 1 minus 1 over n is strictly greater than 1 over n, and there you go. Everyone envies the nth agent, right? So if yes, no. Okay. All right. So that's sort of the thing, and without further ado, we're now at the cusp of talking about some algorithms and seeing sort of simultaneously and sort of in symphony we'll sort of see some existence results for uh, first of all the proportional division. So this is sure, yeah. So this is sort of a would someone like to give it a crack right now? So obviously I can't give the whole second half to a single agent. What can I do? I yeah. So again, if I allow like non-contiguous pieces, then so the exercise is simpler. I actually want a if I want to set a higher goal for myself, I want a allocation in the sense that I want to partition it into n pieces where I achieve this. Okay. Yeah. Perfect. So you have to be slightly careful because the density here is slightly less than 2. So even if you like give me 1 over 2n, it's slightly less than 1 over n. So you can't like give the whole thing. But okay, so this is, you can do it. You just have to sort of pick your partitions a bit carefully. But it's a good exercise to sort of figure this out. I mean, yeah. Even without, I mean, I'm armed with a very generic result that NV-free allocations always exist. So I don't even have to look at it to sort of say that one will. But yeah, just think about it. You have to like be a bit careful because the density here is slightly less than 2. So the lengths have to be uh, managed accordingly. But yeah, you can sort of cut it slightly like shorter and deeper and sort of get away with it. Okay, so if so if there's interest, I can actually go over it in one of the tutorials or like offline, but I'll leave it here. Sounds good. Okay, so finally, this is too much of a delay for a computer science audience for an algorithm to show up. So again, I think. And of course, we'll start with proportionality and the sort of message, the punchline being proportionality is much better, much more of a tractable solution concept than NV freeness. In particular, here's the theorem that will prove it's an important enough result to deserve the status of a theorem. It says that again, I'm not specifying that I'm looking at a cake cutting instance with general n number of agents where the valuation satisfies the properties that I have been like boring you with for the past 1 hour. And here's the cherry on top of the cake, is that not only do such fair divisions exist, proportional divisions exist, they can be computed efficiently. I have to be a bit specific about the computational model, but yeah, let's for the time being say the valuations are given as explicit input through these piecewise constant density function. So if it's a general result, but if it kind of eases you, we are for the time being, let's say the valuations are piecewise constant, right? So given those valuations as input in polynomial time, you can always find a proportional division, an allocation that satisfies proportionality. This in and of itself proves that as a fairness concept, proportionality always exists. So it's not only an algorithmic result, it's an existential result wrapped into an algorithm. Okay, so what good is a theorem if you don't know at least 3 proofs of it? But for the time being, we'll look at 2. And we'll prove it via 2 methods. First one is called the moving knife procedure. This is due to Tubbins. And the second one we'll prove is through the even paths procedure, protocol, algorithm. So indeed, they're classic results, almost 4 decades old, and it's probably a good time to sort of so there's a chapter on cake cutting methods by Adel Fracascia. So sort of that's a good reference, particular at least the two procedures that we'll discuss now can be found there. So if you want to read up, it's a good textbook to sort of look at for computational social choice in general, but in particular for cake cutting cake cutting algorithms that we'll discuss. So again, before I actually get to this moving knife procedure, let me re-emphasize that it guarantees a proportional allocation for any number of agents. It's not just 2, it's for n. For 2, we have already seen the cut and choose actually works. It works even better because it gives me an NB-free allocation. So let me write down the pseudocode for it, and then we'll sort of discuss why it works and why it's called the moving knife procedure. So yeah, so at least for the first few algorithms, I'll be like very pedantic. I'll like explicitly write the pseudocode every step. It will sort of help us internalize things. Going forward, if this is too simple, I'll just discuss the highlights of the algorithm and kind of skip over the mundane, like small little details. But at least for the first few algorithms, it's like write it explicitly, almost in form that you can, if you want, you can code it up, so on and so forth. So what I'll do is initialize this number, say some parameter to be 0. So this is like a left cut mark, if you will. And u is sort of or let me call it w. It's just a set of waiting agents. So this is the set of agents that still haven't received an interval. They are still looking to get an interval assigned to them. So let's for now say the valuations are piecewise constant, so given as explicit input, but I'll get to a model where this can be sort of made black box. Yeah, this is a good point. Right. So I'll initialize this mark, say L, to be 0. So at the leftmost edge of my cake, and then I've assigned the set of weighting agents is just everyone is weighting, no one has been given a piece, L is 0. Right, so now what happens is that I iterate and so while I have more than one agent waiting, so I have 2 or more agents that are still that still haven't received a piece, that still haven't been assigned any part of the cake. What I'll do is like loop and so I'll look at I'll ask every agent who's waiting to tell me a mark such. Okay, so this is sort of the most intricate part of the algorithm, if you want to call it that. So what I do is quite simple. I look at every agent that's still in waiting, that's still in the queue, and I'll ask the agent, okay, here's a left mark which I'll keep updating, but now start moving a knife from this point L, hence the name moving knife, and I'll ask the agent to stop as soon as it gets to a point where the value is equal to the proportional share. So as the algorithm proceeds, L will be somewhere here, and for every agent I'll say, okay, you move a knife and stop at xi such that the value that, let's say xa, sorry, and let me stick to I since I've been forcing I upon you. So I start at L, which is my updated mark. I'll ask the agent, okay, you tell me a point, the first point, the leftmost point, where you reach an interval of value equal to 1 over n. So V for this particular interval is exactly equal to 1 over n. Right, so I'm asking the agent, okay, move the knife and stop it when you have achieved proportional value. Okay, so at the first iteration, when L is equal to 0, obviously you'll have many marks. Some will be to the left, some will be to the right. And at this point, what's a natural thing to do? Is the algorithm clear so far? So who should I give it to if you had to make a guess? So what I've done, let's look at iteration 0. So L is equal to 0. Everyone puts a mark. So this is the first iteration. This is my cake. So agent 7 says, okay, if you give me this much, 0 to x7, I'll get 1 over n, kind of happy. Agent 6 says, okay, I'm here. Agent 2 says, no, look, I'm very calorie conscious, even just this much will give me 1 over n, and so on. So everyone makes such a cut, x1, xi. So what is a smart thing to do here? What is that? Yeah, just give it to the leftmost, right? And you'll, sort of intuitive, look, this is the guy who gets happiest the earliest, wants the smallest piece in some sense with respect to the current left marking L. I'll just give it to this guy and see what happens. So I'll pick I star, which again is Yeah, so what does argmin mean? What does the min operator mean? So argmin means I look at this set, I look at all agents who are still waiting, still in the set W, and among them I pick the one with the smallest xi. Right. So again, it's a very intuitive thing. Like one way to interpret, which is not this algorithm, is I start at L, keep slowly and continuously moving the knife. As soon as someone shouts stop, i.e. someone says I've reached this, the piece now to the left of the knife is of value 1 over n to me, I cut the cake here. So again, at 0 I'll keep moving from here. X2 will be the first person to shout. Okay, I've got 1 over n, boom, the cake is cut, the process repeats, right? So now I'll update L to be xi star, right? So this goes to I. So in particular, this means that I star is out of contention. I have assigned right, this was the mark specified by I star. So in this example, it will be x2, 0 to x2. That's the interval that's given to the second agent. So I cut this cake. I now am left mark is here. I'll only work to the right of it. This interval goes to I star. And I star is happy, is out of the waiting set. Yeah, no tatkal required. Boom, boom, boom. I keep iterating. Right. So again, like if two of them shout at the same time, if then I break ties arbitrarily. For example, I can just give it to the smallest index. So say I'm moving it and both of them say, okay, stop here, doesn't matter. I give it to exactly one of them. The other one still continues to be in the waiting set. Right. So when will it happen that bunch of agents keep shouting together? Can you give me an example where this happens? The case that the cut happens, like the cut coincides all the time.